Hello, this is Dr. Strickland. In this video, we will investigate the alkylation of the alpha carbon of carbonyl compounds. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the things we will do together in class. So we know that alpha halogenation will allow us to turn the alpha carbon into an electrophile. But what if you wanted to make the alpha carbon nucleophilic? Turns out there's a way to do that too. It all starts with using LDA, which stands for lithium diisopropyl amide, to form the enolate ion. So this is LDA right here. There are the two isopropyl groups, and a nitrogen that has two non-bonding pairs of electrons and a negative charge is called an amide ion. And I have no idea how it got that name, but that's what it looks like. All right, so what I want us to look at is the difference in which side of the equilibrium is favored by using these two different bases. Because we know that a regular old ketone, cyclic or acyclic, has a pKa of about 20. All right, so if you're going to find the predominant side of an equilibrium, you have to look at the proton donor on the left side versus the proton donor on the right side. So on the right side, if the reaction were running in reverse, this water would be the proton donor, and the pKa of water is 15.5. Okay, so which side of this equilibrium is favored? Well, it's always the side that has the weaker acid, and the weaker acid has the larger pKa value. So if this is the predominant side, that's bad because you'd need a high yield of this enolate ion to take it on. So if you have the reactants side preferred, then at best you would have a low yield. So low yield of products because the left side of the equilibrium predominates. Because it has the weaker acid. All right, now sodium hydroxide is a great thing to use because it's readily available, it's inexpensive, it's easy to work with. LDA is much more difficult to work with. It's much more expensive. But when you look at this guy over here, who's the proton donor to the right of these arrows, this is an amine. Amines are horrible acids. It has a pKa of about 36. So it's a much weaker acid than that. So we'd have a high yield of products because the right side of the equilibrium predominates. The side that has the weaker acid is the one that will be most will produce the higher percentage of the stuff in the reaction mixture when the reaction is over. In fact, if the weaker acid has a pKa that is 10 units or more above the other one, then it's essentially 100% yield. All right, so we're going to apply that down here because carbonyl compounds with one alpha carbon can be alkylated. That is, you turn this alpha carbon into a nucleophile and then run it through an SN2 reaction with an alkyl halide. And you can do that with aldehydes, with esters, with nitriles, and with ketones that are either symmetrical, so that you have two identical alpha carbons, or whatever's on here to the right of the carbonyl carbon has no alpha hydrogens, like a benzene ring or a T-butyl group. So it will work in those situations also. If you treat this with LDA, you make the enolate ion by deprotonating at the alpha carbon and then follows with an SN2 reaction. Now, because SN2 reactions prefer less hindered places, generally, this will be a methyl halide or a primary alkyl halide, most commonly. So the second step in all of these general reaction patterns is the same. Okay. So the alpha carbon here will have a hydrogen replaced by this group right there. And it's the same thing all the way down. All right, so I want you to take a look at these two practice problems over here. I want you to use these general reaction patterns to predict the products. So pause the video and draw the structures of the products and then come on back. All right, welcome back. So if you did this reaction with this particular ester and bromomethane, then we're just going to replace one of those alpha hydrogens with the methyl group from the alkyl halide. So right here, and you can write it as a CH3 if you wish, like that. And it would be a great idea to go back and name these things. Name this ester, name that ester. Come on down here. This is a symmetrical ketone, so you could have chosen either side. I'm going to go with the left side, but you could have done either one. And so the product that we're going to make here replaces one of these hydrogens with this ethyl group. And you can draw it in skeletal structure, or you can draw it like this if that helps you remember that this ethyl piece came from the alkyl halide. All right, so as long as your ketone has either one set of alpha hydrogens or it has two identical sets, that's the whole story. But there are lots of unsymmetrical ketones. And if we want to be able to choose which one of these alpha carbons gets alkylated in an SN2 reaction, then we need to be able to choose which side has the hydrogen removed from the alpha carbon. So we find, if you come here to the right first, that if we treat this compound with LDA at 0 degrees, we're going to make an enolate ion that looks like this. And I'm drawing the second resonance contributor of these enolate ions. This is called a thermodynamic enolate. And the thermodynamic product will always be the more stable one. And it's because it forms the more substituted alkene. In the enolate ion. Now that does involve the warmer of the two temperatures. So I'm going to put warmer in quotation marks because I don't think of 0 degrees as being warm, but it's a whole lot warmer than -78. If I use the much colder temperature, I get the enolate ion formed with the other alpha carbon. And we have the lithium cation in both cases, and that methyl group is still there. This is called the kinetic enolate, or the kinetic enolate ion. Kinetic means it's formed the fastest. So it's formed faster. by removing the alpha hydrogen from the less hindered alpha carbon. And this will take place at the colder of the two temperatures. Okay. And then you could treat it in a second step with whatever methyl halide or primary alkyl halide you wanted. And you would add an alkyl group to this alpha carbon on the thermodynamic enolate or to this carbon on the kinetic enolate. So take a minute to answer the question at the end of this video and then come on back.